Okay, here is question 77 from chapter 12. This is a question very much related to the last one, 73, that we did. This time we've got two components. So we are going to look at a solution that has chloroform and acetone. All right, so we've got the mass of chloroform is 4.08 grams. Okay, mass of acetone is 9.29 grams. Vapor pressure at 35 degrees of chloroform. Okay, so equals 295, 5 torr, and acetone is where are we here? 332. Okay, those are the pure pressures of both the components at the same temperature. Doesn't matter the temperature; it just matters that they're both at the same. The experimentally measured total vapor pressure of the solution at the same temperature again was P total was 312. And the question wants us to make a comment about the ideal or non-ideal results of our comparison between the vapor pressures. The technique to do this for the question here, what the assumptions we're making is sort of an extension of the Raoult's law to generate several partial pressures of different components and sum them together using Dalton's law of partial pressures. And Dalton's law, if you don't remember, is that the total pressure is the sum of all the partial pressures, however many of them you may have. So partial pressure J to N. Okay, so that's this is Dalton's idea here. And in this case, all of our PJs are going to be of the form PJ is the mole fraction of J times the pressure of pure J at the same temperature. And since we're all looking at the same temperature again, doesn't matter which it is. Okay, so we're going to get our mole fraction first. And because we've only got a two-component solution, then we can get one and calculate the other from that. And then we will calculate all of our individual pressures, and then we will see whether we're above or below or equal to this 312 that we measured experimentally. Okay, let's make this happen. So let's calculate the moles of... You know what? Forget it. Let's just go for a mole fraction. What are we waiting for? So let's do it of chloroform. So we're going to get 4.08 grams. And we're going to divide that by... Yeah, it's like... I never write my numbers down for these things. Okay, so chloroform is also known as trichloromethane. That's the molecular formula for it. So we're 1 carbon, 1 hydrogen, and 3 chlorines. Okay, so that is 119.368. 0.368. Okay, and we're going to divide that by the sum of all the moles in the system here, right? So we have to put chloroform down here again. Trichloromethane kind of just sounds better, and just chloroform just has such a bad rap. Okay, that and 9.29 grams of acetone. Okay, molecular formula for acetone is CH3COCH3. All right, so we are going to divide this by, of course I don't have this either, plus 1.8 times 3. Just calculating CH3 once. Whoa, that's not right. Sorry, excuse me. Plus 3 hydrogens. That looks better. We have 2 of those plus 1 oxygen. 46.068. That is reasonable. Oops. Okay, 46.068 grams per mole. Okay, so that's going to give us our mole fraction of chloroform, which I did calculate beforehand. And the mole fraction of chloroform was 0.1760. Right? And again, it's good to keep track of these things. See, we've got 3 significant figures for all of our values over here. Right? Keep track of where you're at. All right, so the mole fraction of acetone, because we've only got 2 components, is going to be equal to 1 minus the mole fraction of chloroform, which means we're subtracting this from 1. So 1 minus 0.176 gives us 0.824, right? So that's excellent. These are both important values, so I'm going to write them up here and make myself some room so we can clear the board down here and then calculate these things. So we had 0.176, and for acetone, 0.824. Right, we're confident down to there. All right, let's make these disappear. Okay, and let's calculate some pressures. You could break these separately if you'd like. There's no reason why not to. I'm not going to do so. This is equal to the sum of your partial pressures, right? So partial of chloroform and the partial of acetone, and this is equal to your mole fraction of chloroform times your vapor pressure, right? Chloroform plus the mole fraction of acetone times the vapor pressure of pure acetone. Right, it means we're multiplying 0.176 times, where is this thing? 295? Is that a 9? That's terrible. 295, yeah. 295. All right, plus, oops, our mole fraction of acetone, which is 0.824 times 332. 332 torr. And I calculated beforehand a total of 325.4 torr. All right, which is interesting. We're calculating a number. This is our ideal number here, right? So this is ideal, right? This is assuming a linear behavior between the amount of a component that we have in it and the vapor pressure it itself produces. So that's very idealized. And our real value, again, is 312 millimeters of mercury. This is our real value. So this is a much lower value than this. And that tells us that we have very strong interactions between chloroform and acetone in the solution. To just put that in perspective, this isn't a graph. This is going to be a pictorial representation again. So if we have, this is the liquid phase here, right? That much of that, and we'll put the acetones will be purple. Why not? Okay, so there's the acetones. These are not drawn with equal mole fractions or anything like that. If these had less interaction, like if there was less interaction from acetone to chloroform than there was from acetone to acetone, this would have to be a stronger vapor pressure than what we predicted. Right? The real one would have to be predicted, or would have to be higher. Because it's lower, that means that these are interacting very strongly together. Right? That means that acetone and chloroform have very strong intermolecular forces between them. Stronger than those between chloroform and acetone molecules. And that is why we see a lower real value for the vapor pressure than that we calculate with Raoult's law inserted into Dalton's. All right, and there you go.